Okay, all right. As I mentioned, part two. So I came back to answer some of my own questions. I really didn't take the next one, but all right. So the first part of it was explaining the parallel lines. I know that for some people taking algebra and whatever, yeah, you probably have seen that if you subtract the, let's say, 3x plus 5 equals, I don't know, 3x plus 2 or something. You found out, well, if you can subtract all the 3x's, then you're left with 5 equals 2 or whatnot, and that doesn't give you anything. For example, if let's say you have a guy who doesn't remember this guy who runs. In terms of will they be able to catch up, it's like saying, will they get an equal number of speed where eventually one can tag the other and whatnot. And at least for lines, specifically for people, when someone's faster than the other, there's a delta between where the person currently is and then where the person is actually at, in a sense. So with lines specifically, it's not that okay, once the other one becomes 6 and let's say the other one always stays at 5, then no, that won't happen with parallel lines. You will always have a specific amount of speed that you will never be able to surpass. If the lines were equal, then at some point you're not saying that these two are parallel. It's okay, then one eventually will cross. That's basically what the equal numbers are. So here's the proof of for vectors specifically how that works. So I wrote out two vectors here, and then I'll later show you on the screen. So vector A is what I'm calling it, it has these points where it starts at 0 and whatnot, but it has the vectors at the x value of 3, a y value of -6, and a z value of 15. Oh, wait, sorry, that's vector B. That's vector B. Okay. Vector A, my bet, is x value of 1, y value of -2, and a z value of 5. And then vector B was 3, -6, 15, x, y, z. And what you can do with vectors is you can factor out, just like anything. And when you do factor out for vector B, you get 3 times 1, and then for the y value, -2, and then for the z value, 5. It's vector A. This is technically the standard basis vector, which means this is because it's 3 values, actually. You know, I'm gonna do this. So one sec. Okay, so these are the standard vectors. So for I, which is for the x value, you will go up only one step on your x-axis, or to the right sense, essentially. So 1, 0, 0. That's as far as you will go for that. That's what this means. It is I'm only moving one step to the right on my x-axis. For the j, the standard is 1. So this means 2 times 1 step, or 2 steps on my y direction. But because we're positive, we go up. For the 5, oh wait, that's a negative, sorry. So that means we're going 2 steps down. Okay. And for the 5k, so the k, what this really means is this is the z-axis, so diagonal, or if you wanted to view the z-axis, it's like penetrating the screen. Is we're going to move 1 step this way. So let's just say going forward on the diagonal or the z-axis is this way, and then going backwards is penetrating the screen. This means I'm going to go 1 step this way. But that 5k means now you're going to do that 5 times. So instead of just 1, it's 5. So if you always see it just like this without any constant, just means just move 1 step, depending on the variable. And so that's what that means. And then for value b, this is how it was written, and I changed it back to here, the standard basis vectors. This is 3, -6, 15. And you can factor out to have it like this. And this is just like vector A. The only difference is vector B is 3 times as big as vector A. So you can play the factoring game, where if that's true, then what I did was I substituted the letters. So instead of having that I with the I, J, and K with that weird little hat, I just said, all right, if I know that I stands for the X values, the J stands for the Y values, and the K stands for the Z values, just substitute the letters I, J, K for X, Y, Z. And that's what I got here. So this is vector A right here, which is the 1, the -2, and the 5, but now I substitute the I, J, K for the X, Y, Z. And here's vector B, which was 3I, so 3, 1X, the -2J, or the -2Y, and then the 5K, which is the -5Z. And what I said was, okay, then let's factor these out. So factor. So this is divided by that. That's 1. And I'm left with 3. 1 equals 3, which means that's not equal to each other. So that means we're going parallel. The only difference is this is 3 times as big. So no matter how far I go, I'm always 3 times longer. So and if we had to apply it as a run, like if 2 people were running, it's like saying runner B is going 3 times as fast as runner 1, so you'll never catch up. I know it's not the best analogy, but that's how I would put it. Is you're going, your constants will never amount to equal. So you're never going to find a place where, okay, now you're good to go. Magnitude length. So it's like saying you have 3 times bigger. So 3, and in runner terms, you're 3 times as faster. So you'll never catch up. So that's kind of what it is. So that's why things are never parallel theorem. And now the law of cosines theorem, because I know that there's a lot of trig cosines theorems, sine theorems in calc 3. And for me, I always just have a little bit of trouble wrapping that around my head, because I see where it comes from. I'm like, why? Why? So I looked up for something that was similar to vectors, and here it is. So because I don't like it when people just give me the cookie cutter thing. I like to play around with it. But this is the theorem that gives a lot of cosines. C squared, what does it say? C squared A squared plus B squared minus 2AB cosine theta. Okay, great. But why, how, where did it come from? How come? So that was the part I was trying to explain, but I knew I was going to take way over time because I only had like 4 minutes left. So what I did is, let's say we made a regular triangle. So something of a, what do they call it? Like a scalene triangle. So scalene, I thought, scalene triangle. So that was the original, but now I fixed it. So these are the triangles. But now let's say, but because we're using vectors, what we can say is each line is a vector. So each line has a direction and a length. And this is vector A, this is vector B, and this is vector C. So our question is, okay, if we know vector A, and I chose the direction of these vectors arbitrarily according to the video. So vector A goes this way, and vector B goes that way. Cool. But this is vector C. But is it vector A plus B or vector A minus B? So in that sense, we have to find out, but what direction does the vector C go? Or is it going to give us something that we can say that gives us something of a bigger number, or does that mean if we were to add all 3 vectors, we would go to 0? Well, what does that look like in a sense? And if we were to test it out, what we really could say is, okay, then I tried vector A minus B, and what we ended up getting was a neat formula that says, where is it? Right here. So this is vector A that goes up minus the vector B, which means we're going in the opposite direction of what the original thing in the vector said. And we would get vector A minus B, which is the C here. So in a sense, these two, when we subtract them from each other, we get C. But because we can also rearrange the vector C, A minus B, and see which one's the bigger one, you find out that vector A of our original triangle is the bigger vector, or the one that has more length. And so that means the vector C equals vector A minus B can also be rewritten as vector A equals vector C plus B. So that means the vector A is the biggest line. So when we draw the new triangle out, that explicitly tells us, all right, what will, if we were to add all 3 vectors, what would it give us? The vector C must point towards the vector A. So it looks funky here because I tried drawing it in, but when we subtract these two, these vector C points back up to vector A. So in a sense, we could say that, if we were to add all 3 vectors up, this would give us 0. Because vector B is negative. And with that, here's the proof. Sine squared plus cosine squared equals 1. That's a theorem that I know with heart and soul, that I know that one works. And because we have vector c equals vector a minus b, that means we can square both of them. I think I mentioned in the previous video where if you square two vectors, you do not get a new vector. What you get is the length of the two vectors that you multiply together, right? Because essentially all the vector is direction and length. But if you're multiplying the same vector twice, you're just getting double the length of whatever the vector was. That's why it's not technically it's kind of a new vector, but it's the same direction. You're just getting a different length in a sense. But if we can square the vector c, which was vector c equals a minus b, then that means if we square vector c, what we get is vector c times c, which gives us the length of the new vector squared. But remember, vector c is just the same as vector a minus b, so it's vector c times c. And if we were to distribute that out, it's literally vector a minus b times vector a minus b, or vector a minus b squared. And if we were to distribute everything out, remember, when we square two vectors that are the same, it's not a new vector. It's just because the direction is the same, it's just the length doubles. So, the length is squared. So a squared minus 2ab, and those are still vectors, 2a minus b, minus 2 vector a times vector b, plus the magnitude b of the vector b squared. And then and because in here, as I mentioned, now I understand by the law of cosines, because you start here, now you have to go up, push up, and this is where your cosines comes in. Here's why cosine, because there's going to be at some point where you want your cosine, to have a triangle, you cannot have it to be sine, because if you have sine theta 0, where's the third line? No, so you have to go up in some sense, and you can go, and to go up, you need to have at least some sort of value. That's why cosine is useful, because if you have cosine 0, it's just 1, so you can still proceed. And then obviously at some point your cosine will be whatever you plug in the theta, you will get 0. But it's better to have it somewhere where now you have some sort of third line at least that you can leverage on. That's why it's cosine. That's when the cosine theta comes inserted, which after simplifying everything, it's c squared, or the length of the two vectors of c squared is going to equal the magnitude a squared, or the length of the two vectors a squared, plus the length of the two vectors b squared, minus 2 times vector a times vector b times your cosine theta. But here's the thing. When theta is equal to pi half for cosine pi halves is 0. So when you do that, you will get, do this. So 2ab, remember, if cosine theta is pi halves, cosine theta pi halves is 0. So 0 times whatever this is, doesn't matter, it's 0. So all you're left with is the magnitude of c squared plus a squared plus b squared of the length of those two vectors that they were squared. That looks like the Pythagorean theorem, which we need for a triangle in a sense. So that's the proof, which in some sense it still takes me just a little bit of wrap around, but now I see where we would have, if we just stuck with one formula and we tried peeling it apart, specifically with the affine vectors, we have this. So we can do, here's the triangle that I had right here. So I'm going to do something quickly. Here's your angle. There's another angle, and there's your right triangle side. That's how it works. All right. So At least for me, I feel convinced now that okay, that's why for vectors we use that cosine, and why when plugged in all together, specifically for vectors, that's why it works. Because I just like I'll write it down, but I don't believe it until I see it for myself. That's just me. So yeah. All right, and then the last theorem that I was where did I leave that theorem? It was section 11.3, the dot product. Okay. Oh yeah, here's the dot product. Here's the theorem. There's a theorem that for properties of vectors in 3 dimensions, where okay, I would technically need to start all the way at the beginning, but let's say for vectors, how vectors, the angles for vectors in 3D, just like the one for the law of cosines. This one was, yeah, this one was how you can find the angles for just vectors in general, but now what if we apply to 3 dimensions? Well, then you have your x, y, and z axis. Then you have 8 octaves or 8 areas where your x and y, z, and values may morph into different things. And when you want to talk about the angle for specific axes, there's three Greek letters. Alpha, which is the weird A, that one's for the x-axis for angles that are rotating on the x-axis. For beta, that's for y-axis, gamma is for z. And the way you go from it is, let's say you have to start from the positive side of the axis to wherever your vector is. So I actually have a picture right here. Probably not as clear as I want to do, but this is the vector in I guess dotted lines. And yeah, this is the positive x-axis. I know I wrote the x for here. So you go from wherever that is to the vector, from the positive side, from the z-axis to the vector, and then for the y-axis, from where is it, right here, to the vector. So that's the alpha, beta, and gamma. And okay, yeah, this I just wrote myself the octanes, the direction angles. Yeah, you would go from wherever the vector is and that to the magnitude. Where does that theorem come from? Okay. Hold up. Let me look for it. Aha. So yeah, right here. Okay, so this is definitely more than the anticipated. Yeah, this section is more built into this, but essentially, I would have to go all the way back here and explain to you this is the proof of a theorem that basically explains if you with using the law of cosines, if you wanted to find out what cosine theta was, specifically if you had these vectors and what theta would be, if you wanted to determine if it's parallel or perpendicular. Parallel as in the essentially are they just scalar multiples, and then orthogonal. Well, orthogonal is just another word for perpendicular. It's just a fancy word, so I wouldn't be so concerned there. Yeah. Orthogonal is a fancy word for 3 dimensions or perpendicular. So like that. Essentially, one of the theorems was cosine squared alpha plus cosine squared beta plus cosine squared gamma will give you 1. This took me a little bit to wrap my head around, but the way I would say it is, if you had a vector that started from, let's say, the origin to, I don't know, 1, 2, 3. In a sense, you could say, all right, then you have your x values you have to consider, your y values you have to consider, and your z values you have to consider, plus your unit, the standard base vector, which is all right. It can move up 1 unit to the right, 1 unit up, and then 1 unit diagonal. That's your, in a sense. And you would start there up to whatever those points were. But with that bearing in mind, what you can also say is that if you wanted to find the you wanted to essentially find what the because you can make triangles out of that, by the way. And that's essentially what it is if you have that angle and you end up going to where that vector is, you can draw a line in a sense. Actually, let me use that graph that I have. So you can essentially, from here, you can essentially make, oh, this is a triangle. There's a triangle. And there's a bunch of triangles right there. So in some sense, you can say, oh, wait, then what are the sides? What's adjacent opposite hypotenuse? And you can do that with the cosine angles. And for cosine alpha, it would be the x values over the hypotenuse that you make to find the angle of that on the graphs. And then cosine beta, it'd be your y values over the r. And then for cosine gamma, it'd be the z values of your zx's over the hypotenuse used to make for that triangle to find that angle. And then you can manipulate equations around. So cosine beta, and then you would have your r times cosine alpha x, your what is that? Yeah, the r times the cosine beta for your y, and then r times cosine gamma for your z. And then there, what is your r actually? And your r is just essentially the length of that vector. R is the length of that vector. Because you already know what the values are. It's depending on whatever it says. If it says stuff at point there, x, y, z, that's the value. But the r is your length of that vector that you have. And this is what I mean. So yeah, this is the page. This vector right here. If I do for y, yeah, y is right here, beta. I make a triangle right here. This would be the angle right here. But then right here, your hypotenuse. All that there's your vector right there. And whatever that is your length. So whatever you go up to in a sense. So yeah. And for this one, same thing. Boop, boop, there you go. There's your hypotenuse. It's that length of that vector that's right there if I were to draw a triangle out. And for those who do know how to find the magnitude or the length of that vector, it's the difference of your x values. So let's say if it was a position vector and it went up to 1, 2, 3, it'd be 1 minus 0. A position vector, by the way, it starts at the origin, so 0, 0, 0. Let's say I ended at 1, 2, 3. So x1, y2, z3. 1 minus 0, 1. And then 2 minus 0, 2. 3 minus 0, 3. I would square those numbers. I would add them and square them. So 1 squared, 1. 2 squared, 4. 3 squared, 9. So 9, 4, 1. 14. And then square that. So square root of 14. That would be my r. However, because it's squared, the cosine squared alpha, cosine squared beta, and cosine squared gamma is similar to the sine squared plus cosine squared. But now we're considering 3 actually, so if the regular one was a little bit difficult, and this one's I guess not necessarily strange, but it's something to grasp head over. X plus y plus z squared. Where was I? The r, which is the length of or the magnitude of that vector, is similar to the standard basis unit. So that symbol I, j, and k, like the x squared plus y squared plus z squared. Here, because it's cosine squared alpha and whatever, you square everything. So r squared is at the bottom because it was at the cosine beta y divided by r. And then at the top was the length of the hypotenuse, which was x squared plus y squared plus z squared over square root. But because now we square it, we get rid of the square root. So r right here, x squared plus y squared plus z squared, and this is equal to r of the magnitude or the length of the vector. But because we square r, we square that away. So all this pretend the square root never existed. So we would have that, and then the r squared. But because they're both the same, r squared is the same as this, or r is the same as that. But if r squared, but if this was r squared, that means this would be this without the square root. So they're both the same. That's why it equals to 1. And that's why at the top, cosine squared plus cosine squared alpha, cosine squared beta, cosine squared gamma. That's, if we had to break that all apart, it would be the value of your i's of your I values, then your y values, then your z values squared. But if you add them all together, if you were to add those numbers individually all together, you are essentially saying I am going to find the length of all those you're going to find the length of the vector squared, which is just the same as essentially finding, yeah, it's literally the same as finding the magnitude of the vector, which is under, because that is essentially what you're using as your hypotenuse. So that's why it equals to 1. And that took me a little bit to wrap my head around, realizing, oh, okay, so then this can essentially expand itself. So I probably might need to invest in something like a digital whiteboard or something, so this might make more sense. But that's how I put it in audio terms and with my paper. But that's the first 3 lessons of that. I'll come back next with the cross product, and I'll probably start moving on to what's called the calculus of the vector functions and then partial derivatives, although I've gotten a sense of them already a little bit. Although, why not? Let's just rehone the skills of that. But yeah, I'm very excited with the vector function and the partial derivatives before I start moving on to things like polar function, whatnot. And yeah, so let's get the 7-week sprint done. So that's the beginning. So good.